Hello, Analysis 1A. Here we go. This was the homework that you were supposed to do during the asynchronous learning last week. So, okay, I made this ridiculously long video that you were supposed to watch on, say, Tuesday. And on Wednesday, while teachers were learning how to come back to school, you were supposed to do some follow-up homework, and basically what we learned in that video was the derivative of sine, the derivative of cosine, and the derivative of e to the x. Like, that's kind of it. In my video, we also learned the derivative of natural log and the derivative of 2 to the x, but the textbook doesn't teach that stuff until later, so these textbook problems are from this same section. This is still section 3.2. And here we go. The very first thing I asked you to do is problem number 116. And problem number 116 just says to find the derivative of cosine. So, what is the derivative of cosine? Well, we conjectured that the derivative was negative sine, and we conjectured that just from a picture. But we should also just do the proof kind of once and for all. So I'm going to do the boring proof. I suppose I hadn't actually planned to do the sort of awesome geometric proof, but maybe I will. Okay, anyway, here we go. This is more just a test to see if you can do this kind of thing by yourself. So we did one together in the video, so this was now your turn to do it by yourself. Okay, what's the derivative of cosine? Well, the limit definition says that it's the limit as h goes to 0 of cosine x plus h minus cosine x all over h. And so this is going to be kind of like another big sort of limit algebra fest. Alright, let's go. I have to use cosine of a sum formula, so let's do that. This becomes the limit as h approaches 0 of, what's the formula for cosine x plus h? Well, it's cosine x cosine h minus sine x sine h minus cosine x all over h. And I guess it's really kind of like almost the exact same thing. It's really almost the exact same thing. It's almost kind of surprising to me. But yeah. Here I once again notice that there is a sine h over h, which I know goes to 1 as h goes to 0. It's why I call this the most important limit in all of calculus. So let's split this limit up into 3 limits. It's on the one hand the limit as h goes to 0 of negative sine x sine h over h plus the limit as h goes to 0. Well, if I remove that middle term, then what's left over? Cosine x cosine h minus cosine x all over h. And okay, you know, that's sort of it, right? We're basically done, because here I can pull out a negative sign. This is the limit as h goes to 0, so anything that doesn't have any h's in it is a constant as far as that limit is concerned. And so we get negative sine x times the limit as h goes to 0 of sine h over h, plus what can we do here? Well, I can factor a cosine out of the numerator, and in fact I'll just take it right out of the limit for the exact same reason that this is the limit as h goes to 0, so cosine x is a constant. So I get cosine x times the limit as h goes to 0 of cosine h minus 1 over h. Okay, this time I guess for simplicity, maybe I will just use facts now that we've seen already 5 times. Instead of proving that this is 0 for like the 5th time, I will just suppose that you know that now. That does go to 0. This of course goes to 1. That's the most famous limit in all of calculus, and so there it is, right? Our answer is indeed negative sine x. Okay, rushing that a little bit, I feel like that's a pretty decent proof. Is there enough space on this board to prove this geometrically in a way that provides deep understanding? I don't know. Let's see. I will make my picture now. What's it going to look like? Well, I haven't actually practiced this or planned this or anything, so I'm sure it'll go great. Is that even, how bad is that circle? I feel like it's more like that. that might be even worse. Whatever. Okay, so there we go. Here's the unit circle. 1, 0. What am I doing? I'm trying to find the derivative of cosine. So let me take a certain x value. Let me just think about this slightly before I begin. And then a little bit more. So I want it to be, well, I don't know, maybe I won't think about it. There it is. This is my angle x, which really means that this arc has length x on the unit circle. And then what happens if this, and then of course, what's cosine? Well, I can drop a perpendicular down, and this blue thing here is cosine x. So maybe in blue here I'll say, okay, that, by definition is cosine x. Okay, and now the question is, if I want to know what the derivative of cosine x is, maybe I'll write this up here or something. So what is the derivative of cosine x? Well, it's the change in cosine, or maybe I'll just write it like that, the change in cosine with respect to a change in x. And so what does that mean? It's cosine x plus delta x over delta x. So it's how much cosine changes with respect to an infinitesimal change in x. Okay, so let's let this x coordinate be a tiny bit bigger. So this then perhaps here is delta x. That's delta x, and so sure. So this little angle is delta x, and so I've let this angle get now sort of a little bit bigger, so that this whole thing is x plus delta x. And well, what is there to sort of to say now? Well, I guess what I need to find is the cosine. So I drop a perpendicular. This was a perpendicular, but I'm going to drop a perpendicular down here also. And now what happens? Well, if I'm in the first quadrant, which is might as well be, then of course as the angle or the arc length gets longer, the cosine is getting smaller. And so now we have that this purple thing, hopefully this is showing up, is cosine of x plus delta x. And therefore, the, sorry, this was actually made no sense as I'm looking at this more carefully. What I meant to say is that this is the change in cosine. So it's cosine x plus delta x minus cosine x. It's the change in the cosine. Well, I can already see here that the change in the cosine is going to be negative. What is it? It's just this little bit right here. So maybe just right here in green or something, I'll highlight that this is now the segment that I seek. This is the geometric representation of the small amount by which the cosine function changes. And how do I find this? Well, there's like a triangle up here. Okay, is it really a triangle? Yeah, it's basically a triangle. And what can I say about this triangle? Let's see if I want to draw it in or if I want to draw it out. Does it actually matter? I suppose it doesn't really matter. Give me 1 second to decide if I care. I don't think so. I might as well just draw it like that. But I don't know. Perhaps if I want to be consistent with my old way of doing it, maybe it is more clear if I draw the triangle outside. So let's sort of go up here and go over. Okay, so what have I done? I've extended this line sort of horizontally and this line vertically, and so really it's this little triangle that I need to care about. Well, what did we say about this? This is delta x. This is what I did last time. That's delta x. And this little angle here is x. But since this is a right triangle, this little angle here is the complement of x. It's the angle which added to x makes 90 or pi over 2. And here, this is a right angle because this red thing might as well be like a tangent. And tangents are perpendicular to the radius drawn to the point of tangency. Now, is this red thing really a tangent? No, it's really an arc of the circle. But even at this large scale, this arc of the circle is sort of indistinguishable from a tangent line. And of course, if delta x is infinitely small, then that tiny arc is acting like a tangent. And so I think it's reasonable, if we're doing this the casual way, to call that a right angle and to think of this little thing here as being a triangle. Is it really a triangle? No, it's really not a triangle. But if delta x is infinitely small, then it's kind of a triangle. So this is x. This is the complement of x. Therefore, this is back to being x again, because these three angles have to add up to 180. So, okay, if that's true, then what I have here is this little triangle with two purple legs and one red hypotenuse. The hypotenuse of the triangle is delta x. And so, you know, the skill that I'm just kind of assuming that you have, which everyone should have, but, you know, the thing that you really need to be able to do if you're following these proofs is just almost without even thinking, just if you have a right triangle with acute angle theta and radius r, I kind of expect everyone to just be able to just say, oh, okay, this is r cosine theta and this is r sine theta, you know, just almost just automatically without even thinking. Of course that's true. Use the definition of sine and cosine to to confirm that's what those side lengths must be in order for it to work. It's kind of like decomposing the vector, you know, into its horizontal component and its vertical component. So it's actually kind of in physics when maybe you get really comfortable with doing that over and over again. Well, if that's the level of comfort that you're at, then it's sort of immediate what this little thingy is. It is just sine x times the hypotenuse, which is delta x. So this is delta x sine x. And really, that's all there is to say, right? By how much has the cosine changed? What's the numerator here? It's changed by a negative delta x sine x. And that is why the derivative of sine is negative cosine. It's just, it's everything that you need is just right here. Okay, good. Sort of one down. That was the problem I was essentially asking you to rederive, and you could do it either of these two ways. This to me is what most calculus teachers kind of want. This to me is the one that actually provides deep understanding, but there is a little bit of wishy-washiness here. And I find this to be just like, you know, objectively better, but you can sort of see why some people don't like this, because is this really a triangle? Well, it's kind of a triangle, it's kind of not a triangle, and so it's for reasons like this that geometry was abandoned and replaced, and that's why we got, you know, a limit-based definition of differentiation, but I think both are good. Okay, let me be back in 1 second to do the rest of these. Okay, we are back. The most of this homework was just doing a bunch of problems that were relatively straightforward. So here we go, y equals x squared minus 1/2 cosine x, directions are find the derivative. So this is the most basic kind of problem. This is what calculus students all over America are doing. You know, I just give you a function and you just need to be able to, like, you know, take the derivative by hand. So this is just a matter of, you know, do you know all your formulas and can you keep it all straight? Well, I think we can. What is the derivative of this? This is this mysterious symbol, dy dx, which I will explain more in a later class, but okay, for now, whatever. It's just the derivative of y, think of it, and the derivative of x squared is 2x, and the derivative of negative 1/2 cosine x is, well, it's going to be negative 1/2 times whatever the derivative of cosine is. Well, we just saw that the derivative of cosine was negative sine, and so that's all there is to it. The answer is 2x plus 1/2 sine x. Problem over. 23, y equals 1/2 e to the x minus 3 sine x. Okay, we spent, you know, an hour or something in this video from last week determining that the derivative of e to the x is e to the x. So, alright, now comes the sort of mindless practice. What is the derivative of 1/2 e to the x? Well, it's 1/2 e to the x minus 3 times, what's the derivative of sine? Well, it's cosine. So, that's it, problem over. Boom, boom. 49, 6 root x plus 5 cosine. Okay, well, first I'll introduce one intermediate step where I rewrite 6 root x in derivative-friendly form. What is 6 root x? Well, it's 6x to the 1/2. I think this is a good thing to do for beginners because it shows that the product rule, sorry, the power rule is applicable because this is a power function. It's a function of the form x to the 1/2. So you bring down the 1/2 and you get 3x to the negative 1/2 plus 5 times the derivative of cosine is negative sine. And then you can either leave it like that or rewrite it. I would put my final answer as x to the negative 1/2 is 1 over x to the 1/2, and x to the 1/2 is root x, so normal people would then rewrite it like this. So minus 5 sine x. That's it. Okay, 55 is just another problem. Oh, it's basically a problem that just says take the derivative, but then there's a little bit of an extra step. What is the derivative of x plus e to the x? Well, the derivative of x is 1, and the derivative of e to the x is e to the x. So that's the derivative function. Now they specifically say, what is the derivative at 0? So if I plug in 0 into this formula, e to the 0 is 1, so I get 1 plus 1 is 2. Therefore the slope is 2 there, and alright, they already told me that when I plug in 0 in, I get 1. Okay, that's just true, I've just double checked that. Therefore the equation of the tangent line to this curve at 0, 1 is y minus 1 equals 2, well, 2x, because I was going to say 2x minus 0, but alright, there it is. Crying baby, I'm going to go get him. Okay, that was number 55. 59 and 61 have the same directions. Directions are determine where there is a horizontal tangent. So here we have this curve, y equals x plus sine x on the interval 0 to pi, and the directions are, yeah, like I said, find where, if anywhere, there is a horizontal tangent. Okay, and well, I think this is kind of an exciting problem, sort of, because we did problems like this in pre-calc C. So okay, well first let me just do the calculus. What's the calculus? The calculus says, okay, let's take the derivative, and what is the derivative in general of the function x plus sine x? Well, it's going to be 1 plus the derivative of sine is cosine. So great. And now, what is the question? The question is, where is there a horizontal tangent? Well, there's going to be a horizontal tangent when there's a tangent line with slope 0. So, in other words, they might as well be asking me, you know, where on this curve is there a tangent line with slope 0? In other words, where is the derivative 0? Okay, so hopefully that was pretty obvious that the way to solve this problem is to set the derivative equal to 0. Wherever the derivative is 0 is a place where the slope of the tangent line is 0, and there's going to be a horizontal tangent there. Alright, so this whole problem just reduces down to, where is cosine negative 1, and cosine is negative 1 at x equals pi. And I think you were just supposed to answer at x equals pi, and then the problem's over. But, alright, interestingly, you know, just taking this curve, if you were a simple pre-calculus student and you were given y equals x plus sine x, how much of this could you graph, and how much of this could you not graph? Well, we did stuff like this. Last semester, we said, okay, hey, you know, sine is always between negative 1 and 1, fact. So what can I say about x plus sine x? Well, it's always going to be between x plus 1 and x minus 1. And so our function is sort of bound between these two lines, y equals x plus 1 and y equals x minus 1. And so, try to put some effort into this here, making this accurate. Already changed my mind, because I guess I only want to look at positive x values, so something like that. Okay, sure. Well, you know, I need to have sort of pi's on my scale. So let's make that 2 pi, and that pi over 2, and 3 pi over 2. Then I also want 1 on this picture, so that's 1. That's also 1, and that's negative 1 and negative 1. Alright, why am I doing that? Because I want to graph, yikes, I want to graph the line y equals x plus 1, which looks like this. So there it is. And the line y equals x minus 1, which looks like that. Therefore, sorry about that. Therefore, we can say that our function lies between these lines, because that's what we proved over here. This is all just pre-calculus. What else can we do? Well, we can sort of graph as a kind of like a dotted line or something, the line y equals x, which is going to be halfway between. And then maybe in blue now I'll start to plot this function. Well, of course, if you plug in 0, you're going to get 0. So that's a dot. Boom. When you plug in pi over 2, you're going to get that sine of pi over 2 is 1. So you're going to get 1 plus pi over 2. In other words, you're going to land at pi over 2 on the line y equals x plus 1, because you're going to be 1 more than x. And when you get to pi, what happens? Well, when you plug in pi, sine of pi is 0, so you're just going to land directly, boom. And at 3 pi over 2, sine of 3 pi over 2 is negative 1. And so now you're going to land on the lower part of the envelope. And by the time you get to 2 pi, I see I need to go a little bit farther here. By the time you get to 2 pi, you're going to have landed right here. And okay, so in pre-calc, that's as far as you could go, and then we would sort of connect those 5 dots in a kind of like a zoom, zoom, zoom kind of way. But what I never quite knew was where, if anywhere, this function had kind of like a relative max or anything, and relative min. And now I sort of do know, because what have I just learned? I've learned that x equals pi, my derivative is 0. And so I'm going to have a horizontal tangent line right here. And therefore, I can tell you now that this function, I've learned a lot about the sort of shape of this function. This is kind of a preview a little bit later. So this is going to go up, and then it's going to become flat here, and then touch the lower envelope, and then back up again. So that is now a kind of very, very accurate graph of x plus sine x. More accurate than I was able to do when I was in pre-calc, because now I know that it's precisely here at this point, pi comma pi, I guess is what it is, pi comma pi, in which the function is like kind of flat for a second, right there. Here is this horizontal tangent line, but sort of nowhere else. In fact, this function is always increasing, because its derivative here we can see is always positive, except there when it's 0. So this function is going up and up and up. Alright, that's good enough. Alright, let's do these last two. Same question, but now for negative 4x plus e to the x. Well, alright, once again, I can take the derivative. What is the derivative of negative 4x? It's just negative 4. What's the derivative of e to the x? It's just e to the x. When, if ever, is that 0? Well, I just set this equal to 0 and solve. So this boils down to, when is e to the x equal to 4? This is a little pre-calc review. Take the natural log of both sides, and we get that x is ln 4. So it's at, the answer to this problem, number 61, is at x equals ln 4. The function has the curve has a horizontal tangent line. Okay, 75 says, take this function, 3x plus sine x plus 2, and show that it never has a horizontal tangent. Well, a function has a horizontal tangent if the derivative is 0, so I just need to show that the derivative of this function is never 0. And, okay, maybe this is kind of easy, I didn't leave myself much space. The derivative of 3x is just 3, the derivative of sine x is cosine x, and the derivative of 2 is 0. So I just have to show that, that this derivative is never 0. Well, I'll just set the derivative equal to 0, and suddenly I have the equation cosine x equals negative 3. Well, that's just, not going to happen. So this equation has no solutions, which means that this derivative is never 0, which means that there's no horizontal tangent line. Okay, back in a minute for the last two problems, which are actually kind of hard. Okay, here we go. This is number 109. This problem's actually really easy, but I know that people have trouble with it because it involves a certain amount of reading comprehension. So I copied the problem exactly up here. Find an equation of the parabola y equals ax squared plus bx plus c that passes through 0, 1, so that's fact number 1 about this function, is tangent to y equals x minus 1 at 1, 0. So it seems like they only gave me 2 pieces of information about this function, and what we kind of need are sort of 3 pieces of information. Actually, let me kind of temporarily, just name this function f, because that seems more convenient. And alright, I just need to find out what a, b, and c are, and then the problem is over. Well, one fact is just given to you immediately, that this function passes through 0, 1. Okay, well that means that if I plug 0 into this function, I have to get back 1. But if you plug 0 into this function, then you just get c. Alright, so they basically just kind of told me that, that c is 1. Okay, so that means that this function is ax squared plus bx plus 1. But also, notice that they tell me something about this tangent line, that there's this tangent line y equals x minus 1. But they specifically tell me that my parabola is tangent to this line at the point 1, 0. In other words, built into that sentence is the fact that, the function and the tangent line, go through this point 1, 0. And so it's just also true that when you plug 1 into this function, you get back 0. So now if I just plug in 1, well then what do I get? Yeah, I just get a plus b plus 1. And that has to be 0. Because 1, 0 is a point on this function, a point on this parabola. Okay, so from this, all I can tell, I guess, is that a plus b is negative 1. So, is there some more information that's going to help me find out what a and b are? Yes, there's some calculus. The calculus is that this parabola is tangent to the line y equals x minus 1, and is tangent to y. Is that how they phrase it? Is tangent to the line y equals x minus 1 at 1, 0. Okay, yeah. So the line y equals x minus 1 is the tangent line to this curve at 1. Well, this line has slope 1. So if this line has slope 1 and the derivative of a function is the slope of the tangent line, then since this tangent line has slope 1, it means that the derivative of this function must be 1 at x equals 1. Okay, so if you followed all that, the other piece of information is that the derivative at 1 of this function is 1. Because at the point 1, 0, with x coordinate 1, the slope of the tangent line to the curve is 1, so the derivative is 1. Well, now I can just take the derivative. What is the derivative of this function using this form where I've already, well, it doesn't matter what form you use actually, but going from there to there, the derivative is here 2ax plus b, and that's the derivative in general. So the derivative at 1 specifically is you just plug in 1 for x, and therefore 2a plus b has to be 1. So now I have a kind of a little system of equations here. 2a plus b is 1 and a plus b is negative 1. Subtract these and I get that a is 2. And if a is 2, then b is negative 3. Alright, so if I did that correctly, it means then that this function is 2x squared minus 3x plus 1. Let's see, does that like factor or anything? I bet it does. And 2x, yeah, I guess it does. 1 x 1, 2x squared minus 2x minus x, yeah. So, and then we can just double check all the facts. If I plug in 1, what do I get? I get 0, check. If I plug in 0, I get 1. Check. If I take the derivative of this function, I get back 4x minus 3, and when I plug 1 in there, I do indeed get 1. So everything's looking good. I can make a quick graph of this. You know, I suppose if you're skeptical, here is the point 1 comma 0. It also has a thing at 1/2, so that's 1, that's a half. This parabola, when I plug in 0, I get back 1. And then there's also this line y equals x minus 1, which is a tangent line to the curve at this point. So what does the function look like? Well, it's going to just be some kind of parabola and something like that. That's pretty much it. Root at 1/2, root at 1. Derivative of the function is 1. So the slope of the tangent line to the curve is 1. So that's it. Okay, be back in 1 second for the last problem, which is actually hard. Okay, here we go. Last problem from this homework, number 111. I say this is hard. It is pretty hard, but this is now the third problem like this, I believe, that we have done. And so hopefully, you know, with repetition, it's getting easier. We have this curve, y equals x cubed minus 9x. I suppose I prefer to just give it a name f, and what are we doing with this curve? Well, we want to find the tangent lines to this curve through the point 1, negative 9. Alright, and I can't stress this enough. If you just really have no idea what you're doing, and you also sort of don't try and don't care or something, it's possible to do this problem completely incorrectly. If you also, you know, don't think and don't make a picture and don't do anything, and that is, you're like, oh, I got my point, hey, 1 comma negative 9, let me just take the derivative, plug in 1, done. That is just completely wrong. We are not trying to find the slope of the tangent line to the curve at x equals 1. We're trying to find the slope of the tangent line to the curve that goes through the point 1 comma negative 9. Notice that when I plug 1 into this function, I just don't get negative 9. What do I get? I get 1 minus 9, so that's negative 8. So it's actually pretty close, but still not right. Is that true? It's kind of crazy, yeah. Okay, so let's make a graph of this function to try to understand what's going on, because I think if you don't make a picture, you could be lost. So what is this? It's x. I'll take an x out, so this is x squared minus 9. Aha, I see. This function is x minus 3, x plus 3. This is a cubic, and I think let me put some effort into thinking this through. Whoa, crying going on downstairs. So there's a root at 0, there's a root at negative 3, there is a root at 3, then way down here at 1, negative 8, so 1, 2, 3, 4, 5, 6, 7, 8, 9. At negative 8, there is a point 1, negative 8, which is on the curve. But then there is a point 1, negative 9, which is not on the curve. And so, okay, let me try to draw this curve then somewhat accurately. It's a little bit hard to do because I'm just sort of, to some extent, I'm winging it, but it's a cubic. It's going to go way up, kind of like way down, or somewhat down, and back up again. So there's my cubic, roughly speaking. And then I have this point, 1 comma negative 9, not on the curve. And what am I trying to do? I am trying to find the lines which are tangent to the curve and pass through this point. So I talked about thinking of this function as kind of like a boulder, and you have a stick kind of anchored to the point 1, negative 9, and you just kind of swing that stick, and wherever it bumps into the boulder, that's the tangent line. And it seems like it's also, there are going to be two of them. One over here and one over here. So I think I'll draw, I don't know which one to draw. Both are a little bit awkward, but I guess I will draw this one. So I'm going to draw in this line, shot. And there's this point. I don't know what that point is. And I also don't know what the slope of this purple line is. But that's the purple line I want. The line which is tangent to the curve and also passes through the point 1, comma, -9. So I'm going to give this point a name, A, comma, and, well, if it's on the curve, then its y-coordinate must be a cubed minus 9a. And now, alright, this is going to be very, very tiny, so maybe impossible to read, but I can actually give you now what the slope of this purple line is, but not, but in terms of a, because I'm going to go sort of like down and over a little bit. And okay, this is very hard to see, so maybe I'll just kind of redraw it in a zoomed in form over here or something. I have this point, 1, comma, -9, and then over here I have this point, a, comma, a cubed minus 9a, and what I want to know is what is the slope of the purple line which passes through those 2 points. Well, the one way to do this, if you're just like an Algebra 1 student, is just use, you know, delta y over delta x. What is the change in y? Well, it's going to be -9. Yeah, well, the slope is negative, so we're going down. By how much do I go down? I guess I should do it the other way then, right? It's going to be, yeah, it doesn't really matter. But if this is my sort of second point and this is my first point, then it's like a cubed minus 9a minus -9. And this is a minus 1. Okay, so if you follow that, I just, you know, just like in Algebra 1, you know, if you give me 2 points, suppose that's my first point and that's my second point, then the change in y, I'll even just write this over here, the slope of this line is delta y over delta x. What is delta y? It's the change in the y coordinate from point 1 to point 2. So you just take the y coordinate of point 2 and you subtract from it the y coordinate of point 1. And so what we get is that delta y is a cubed minus 9a plus 9. And what's delta x? It's just the difference between the x coordinate of the second point and the x coordinate of the first point. So that's how we get a minus 1. Okay, so I haven't done any calculus yet, so it's time to sort of do the calculus now. I can, in fact, take the derivative of this function. Maybe I'll do it here. So what is the derivative of this function? The derivative of x cubed minus 9x is 3x squared minus 9. And that was easy. So now that I know the derivative, what I care about is specifically what is the derivative at a. And if I plug a into this formula, I get 3a squared minus 9. And so it's also true that the slope of this line is 3a squared minus 9. And so the solution to this problem is to say, all right, well, on the one hand, there's this point A where the line is tangent. I still don't know what A is, but the slope of that purple line must be 3a squared minus 9. But on the other hand, it must also be a cubed minus 9a plus 9 over a minus 1. And now I have a single equation. And if I solve this for a, that should tell me what that point is. Okay, so let's just do it. Maybe I'll even just do this in just slowly. So 3a squared minus 9 times a minus 1. That seems like the obvious thing to do. And then this is going to give me 3a cubed minus 3a squared minus 9a plus 9. Equals a cubed minus 9a plus 9. So, assuming I've done this correctly, the 9's cancel and also the negative 9a cancels. And so it seems that I just have, 3a cubed minus 3a squared equals a cubed. In other words, 2a cubed minus 3a squared equals 0. Factoring an a squared out of this gives me 2a minus 3 equals 0. And therefore, seemingly, I have two solutions to this equation. a equals 0 and a equals 3/2. Okay, let's explore them both separately, a equals 0 and a equals 3/2. Well, a equals 3/2 is pretty consistent with the point that I have drawn here. That looks like about 1.5, or at least that's plausible considering I didn't try that hard to make a good graph even. Does that all sort of make sense? Well, to really confirm this, unfortunately, I think I need to plug 3/2 into my function. I don't really want to do that, but I guess I could. If I plug in 3/2, what am I going to get? I'm going to get 3/2 times, that's negative 3/2, and if I plug 3/2 in here, I'm going to get 4.5, so that's 9/2. So that's like negative 81 over 8. Yeah, that's not exactly the answer I was expecting, but okay, I persevere, because what is then the derivative at 3/2? Well, the derivative at 3/2 is, using that formula, it's going to be 3 times 3/2 squared minus 9. So let's see what that is. Man, that's 27/4 minus 9. So 27/4 minus 36/4. So that's negative 9/4. Again, negative 9/4 is a relatively reasonable, it's not wildly wrong as an answer. Let me just double check my math. 9/4, 27/4 minus, yeah, I think that's right. Okay, and so finally, what is delta y over delta x then for this problem? Well, it's going to be this negative 81/8 y coordinate minus negative 9, so plus 9, over 3/2 minus 1. So hopefully this is negative 9/4. Is it? Well, 9 is 72/8. So I get negative 81/8 plus 72/8 over, this is of course a half down here. Uh-oh. What is that? Negative 9/8 divided by a half. I am very sad. 9 times 8, 72, negative 9/8. Oh yeah, sorry. Negative 9/8 divided by a half is like times 2. So that's negative 9/4. That's the answer I wanted. So yes, indeed, okay, it took me a little bit of effort here, but indeed I took the point 3/2 comma negative 81/8 and the point 1 comma negative 9, and by computing using algebra 1 techniques I found that the slope of that line is negative 9/4. But negative 9/4 is also what I get when I plug 3/2 into the derivative. So I have confirmed that this is all sort of working. Okay, but I also have this a equals 0 point. What's up with that? Could a equals 0 be a solution? Well, yeah, it's actually very reasonable that a equals 0 is a solution. Of course, when I plug in 0 into this function, I get back 0. So that's nice. What is f prime of 0? Well, that's also easy to do. It's negative 9. And so then finally, I can compute delta y over delta x. Well, the slope of that line is just going to be, down negative 9 over 1. So that's just negative 9. So that just all checks out. So here's what we have. We have this purple line here with slope negative 9/4. Picture's not great, but it's not terrible. And then the other line also goes through the point 1 comma negative 9, but goes through that point and 0, 0. So it's like that is what it's supposed to be doing. Sorry, my line got a little curvy there, but basically something like this. And so this is 0, 0, and this line has slope negative 9. And so there are indeed two lines through the point 1 comma negative 9. with slope, which go through the, there are two lines which are tangent to the curve that go through the point 1, comma, -9. What's this one? It's just the line through 0, 0 with slope -9. So one answer to this problem is y equals -9x. That's one of the equations. And the other equation is the equation of this purple line. 1 second. It is y, literally 1 second, plus, well actually it's going through 1, comma, -9 already. So I can just say y plus 9 equals -9/4, comma, x minus 1. That is the other line. It's the purple one, which is tangent to the curve and passes through 1, comma, -9. Okay, there we go. That's the end of this homework. Really, there was only one of the problems that was hard, which is this last one here. And this is our third or fourth time doing these kinds of problems, so hopefully you're getting good at it. Goodbye!